Hey, Calc BC, welcome to Chapter 2, Lesson 3, Applications of Derivatives, Part 1. So this lesson is going to cover topics from the College Board's Unit 5, Analytical Applications of Differentiation. I highlighted a whole bunch of topics here. This really does dig deep into applications of derivatives. We are going to have two final lessons in Unit 2. And this is the first one. So this is Applications of Derivatives Part 1. The fourth lesson is going to be Applications of Derivatives Part 2. So that's it. And then we're going to have a quiz on Unit 2. And then we're going to keep going to integrals. Again, as with limits, we're not going to hit every single derivative topic in this brief review. But the goal is that we hit the major topics, make sure we have that foundation before we move into anything new. And we'll come back throughout the year and hit on some other topics later on to make sure that we're reviewing throughout the year for the AP test / the conclusion of the course to make sure that we know everything by then, all right? So I'm going to pause this and switch over to the notes. All right, so here are the notes, and you can see here we're looking at applications of derivatives part 1, as I said, and specifically this will include EVT, the extreme value theorem, MVT, the mean value theorem, Rolle's theorem, and derivative tests. All right, so the first thing that we need to know is absolute and relative extrema. So an absolute max in this diagram, if we think about that we have the closed interval, -2 to 4, should be fairly clear that the highest point, the highest y value here is going to be right here at 4,21. The absolute minimum, the lowest y value here is going to be all the way down here at -2, -15. We only have one relative max on this graph, and that's right here. It's in the close vicinity of points. It's the highest, and that's at 0,5. And we have a relative minimum here at 2,1. All right. So that's kind of visually what we're talking about when we talk about maximum, minimum, absolute, relative. We have a couple definitions that we have to read through here. So first off, the definition of a critical number and a critical point. If f is defined at c, f prime of c equals 0, or if f is not differentiable, then c is a critical number of f, and the point c comma f of c is a critical point. So we have a critical number, which is the x value, which we're calling c, and the critical point is the actual point for c, so c comma f of c. The extreme value theorem is next. If f is continuous on a closed interval, then f attains an absolute maximum value f of c or an absolute minimum value f of d for some numbers c and d in the closed interval a to b. And we have guidelines for finding extrema on a closed interval using the candidates test. So to find the extrema of a continuous function f on a closed interval a to b, use these steps. Find f prime and the critical numbers. Evaluate f at each critical number. Evaluate f at each endpoint. And the least of these values is the absolute minimum. The greatest is the absolute maximum. So that's how we find these extrema. So let's try this. To find the absolute maximums and minimums, or maxima and minima, of f on the given closed interval, and state where these values occur. Okay, so let's figure this out. So first off, the first step is to find f prime of x. So we have 6x minus 24. We're going to set that equal to 0 so that we can find the critical numbers. Add 24. I'll try to do this so that you can see. Divide by 6, and we get 4 equals x. So that is our critical number. And so we're going to make a chart of values of x and f of x. And the numbers we want to include are the lowest number in the interval, any critical numbers that we found, which was just 4, and the maximum number in the interval, the maximum x value, which is 5. And we want to know what are the y values for each of these 3 numbers. We don't care about the slope for each of these numbers right now. We want to know what are the y values because we're looking for the maximum and the minimum y values. So we're going to plug -1 into the original equation, and we get 26. So we're going to plug 4 into the original equation, and we get negative 49. And we're going to plug 5 into the original equation, and we get negative 46. So now we just have to look at this and think about, okay, what is the absolute max? And what is the absolute minimum? And the largest y value happens at negative 1 comma 26. The smallest y value happens at negative 49, so 4 comma negative 49. That is because any critical numbers are the only places where the slope can change direction, where the function can change from going up to going down. So that's the only places where a relative extrema could be. So we know that anywhere between negative 1 and 4 is going to have a y value between these two. Anywhere between x value of 4 and 5 is going to have a y value between these two. So these are the only places where the extreme value can be. Okay, so let's keep going with letter B. We're going to do the same idea. So we start by taking the derivative. We set it equal to 0 to find the critical numbers. And I can factor out x squared and 6 as well. So we're left with 3 minus 4x. So we have the critical numbers of 0 and negative 3 divided by negative 4 is 3/4. Right, because we can set each of those factors equal to 0 and solve for x. So if we make our chart this time, we have a minimum of negative 1, maximum of 2, and in between we have our 0 and our 3/4. So it looks like that. And we're going to plug each one of these into the original function to figure out what the y values are. So if we plug in negative 1, we're going to get negative 7. If we plug in 0, we're going to get 5. If we plug in 3/4, we end up with 721 over 128. And if we plug in 2, we get negative 43. I'm just kind of flying through that part because you don't need to watch me type this all into my calculator to get each of these values. If you want to slow down and pause so that you can verify that these are correct on your own, I highly encourage you to do that. But I'm not going to waste your time by making you watch a video of me typing a bunch of buttons into my calculator when I've already calculated it. So these are the y values that we have. So now we need to know what's the absolute max and what's the absolute min. And if we take a look at this, the largest y value occurs at 721 over 128. So that's going to be 3/4, 721 over 128. And just to verify there, 721 divided by 128 is 5.6 something, so that's bigger than 5. And the absolute minimum has a y value of negative 43. So we have 2, negative 43. There we go. So that's our absolute maxes and mins. All right, let's keep going. Next up, we have the mean value theorem. The mean value theorem says that if a function is continuous on the closed interval a to b and differentiable from a to b, then there is at least one number c between a and b. So these are all x values we're talking about. Between the x value a and x value b, there's some x value c, such that the derivative of the function at c is the mean value of the slope, f of b minus f of a over b minus a, the average rate of change. Number 2 is just a reworking of that same thing. F of b minus f of a is going to equal f prime of c times b minus a. That's just the same equation, but we multiply b minus a to the left. And number 3, the slope at c is the average slope from A to B. And I will say that all three of these things are really the same thing, right? These are three ways to write the same conclusion. That's the mean value theorem. There's just some number C with the average slope of the slope from A to B, right? So if we have a curve that looks like this, and we're looking at 2 points, maybe this is A and this is B, and we draw a dotted line between them, then there's some x value C between those 2 points that has the same slope. And in this curve, it would be somewhere around right here. You can see that has the same slope, and that's always going to happen at least 1 point between those two endpoints. All right, my screen is lagging right now, so I'm going to pause for 1 second, and then we'll keep going. All right, so the next thing that we're going to talk about in the notes is Rolle's theorem. So I figured it would be nice to pull up a quick Wikipedia page of who Rolle is and why we named this theorem after him. So this is Michel Rolle. He was a French mathematician alive from 1652 to 1719. He's best known for Rolle's theorem, which is what we are about to learn. It looks like that with an integral, but we're not going to learn it like that today. And he is also the co-inventor in Europe of Gaussian elimination. So you might remember way back from honors pre-calculus, if you took that course, we had a matrix unit. And one of the ways that we talk about row reducing matrices is through Gaussian elimination. This is a big part of linear algebra. So if you ever take a linear algebra course in college, this will come back. But yeah, so he's connected to matrices, which we already learned in pre-calc, and now we're going to learn about Rolle's theorem. So Rolle's theorem is really just an extension of the mean value theorem. The mean value theorem, as we talked about, is saying that from A to B, there's at least 1 point in between with the same slope as the average slope. So Rolle's theorem is specifically true when f of A and f of B are equal. So for example, that on a coordinate plane, if we kind of sketch the similar picture, that would be like if we use this point and this point as our A and our B, because the y values are the same. So there are 3 things that must be true. If our function is continuous on the closed interval A to B, if we're differentiable on the open interval A to B, and f of A equals f of B. So we have this kind of straight across the line here connecting those 2 dots because they have the same y value. Then there is always at least one number C, so one x value C between A and B such that the derivative of C equals 0. And C therefore is a critical number. And C also has a horizontal tangent line, which is obvious because the derivative is 0. And you can see that here in this graph that I drew, this rough sketch, right here. We have the point with the horizontal tangent line. And this is an extension of the mean value theorem because it's the same thing, right? It's just specifically talking about the horizontal tangent line when A and B have the same y value, right? There could be more than 1 point in here that have a horizontal tangent line. This sketch only has 1. If it looked like this, and this is our A and this is our B, now we have 1, 2, 3, 4, 5 places where we have a horizontal tangent line. It doesn't matter. The theorem holds true. We just have at least one number C such that the derivative is 0. Okay, so let's take a look at this example. We're going to show that the conditions of Rolle's theorem are met, and we're going to find C such that Rolle's theorem guarantees that f of x equals x squared minus x minus 6 between -2 and 3 has a horizontal tangent. at some value c. Okay, so let's try this. So first off, we have to see if Rolle's theorem holds true. So is this function continuous from -2 to 3? And the answer is yes. This is a simple polynomial, right? It's going to have curves. It's going to be continuous. There's not going to be any holes or breaks. There's no reason for it. That also answers the question, is it differentiable? It's a simple polynomial. So yeah, it's differentiable. It's only made up of curves, no corners, no holes, nothing like that. And now we need to know, does f of a equal f of b? So does f of -2 equal f of 3? So that's what we have to figure out. F of -2 is going to be -2 squared minus -2 minus 6, which is 0. It's 4 plus 2 minus 6. F of 3 is 3 squared minus 3 minus 6, so 9 minus 3 minus 6, which is also 0. So check, check, check. All three of those things are true. We're continuous, we're differentiable, and f of a equals f of b. So yes, Rolle's theorem holds true, and we're going to find the c that Rolle's theorem guarantees. So the derivative here is going to be 2x minus 1, and we need to know where is this c value. So where is the x value where the derivative is 0? So we're going to set that equal to 0 and then solve. So that's the c. So c equals 1/2. That's the c that makes this true. All right, cool. We're going to keep going. Given the function f of x equals 3 minus 5 over x on the interval 1 to 5. The graph of f of x is shown on the right. Visually, what is the mean value theorem trying to find? So mean value theorem, we know, is looking for the point between 1 and 5 that has the average slope. Okay, so if we sketch that over here, it's between 1 and 1, 2, 3, 4, 5. So x value of 1, x value of 5. What that means is if we connect those with a line, like that, we're looking for the point between these 2 points on this curve that has that same slope, which happens to be the average slope. So you can tell it's going to be maybe right around here. And it's going to have that parallel slope to the original one, which is going to be a slope of 1, it looks like. Yeah. So let's show that the mean value theorem applies and find the c that the theorem guarantees. So for the mean value theorem to apply, we have to be continuous from 1 to 5 and differentiable from 1 to 5. So are those two things true? Let's check. So based on the graph, it looks like we have a continuous function and it's a curve. So it should be continuous and differentiable. If we take a look at this equation, 3 minus 5 over x, that's going to hold true. The only problem is going to be if x is 0, because then we can't divide by 0. So there's going to be an asymptote there. But other than that, we should be continuous and differentiable. There's no reason why that wouldn't work. So we're good. And then we're going to find the c that this theorem guarantees. So our f of x is 3 minus 5 over x, which I'm going to rewrite as 3 minus 5x to the negative 1. So our first derivative, the 3 goes away, and negative 1 times negative 5 is positive 5, x to the negative 2, or 5 over x squared. And so what we want to do now is we know that our average slope is 1, and we could prove that with this, formula. We know that the f prime of c has to be the y values of 2 minus negative 2 over 5 minus 1. So I did y2 minus y1 over x2 minus x1, right? That's our slope formula from back in the good old days of pre-algebra, algebra 1. So we have 4 over 4. So yeah, that proves that our average slope is 1. So now we want to know, when does this derivative equal 1? Because that's our average slope. So we want to know, when does 1 equal 5 over x squared? So I'm going to multiply the x squared to the other side. So we get x squared equals 5. And so x equals plus or minus the square root of 5. All right. So those are the x values where we have a slope of 1. So think about this. We need an x value that's between 1 and 5. So negative root 5 is definitely not going to be between 1 and 5. Let me real quickly just type in square root of 5. It's 2.23. That is between 1 and 5. So our c is positive root 5. And that's going to be the x value of this point that we drew in right here. I said it was 2.23. I'd say that I estimated that pretty well, because it looks like about 2.23 would be that x value. So that's perfect. All right, you can see that. Okay, next up, we're moving on from mean value theorem and Rolle's theorem. We're going to talk about tests for increasing and decreasing functions. If f prime of x is greater than 0 for all x in an interval, then f of x is increasing. Basically, that just means the slope is positive because the derivative is greater than 0. If the derivative is less than 0, then the original function is decreasing, or it has a negative slope. And if f prime of x equals 0, then over an interval, then our function is constant. It would be a horizontal line. Then we're going to expand that to the first derivative test. We're going to talk about those critical numbers again. If c is a critical number of a function, f, that is continuous on an open interval I containing c, lots of letters, but we'll just keep going here. I think it'll make sense as we write this. If f is differentiable on the interval, except possibly at c, then c, comma, f of c can be classified as follows. If f prime of x changes from positive to negative at c, then c comma f of c is a maximum. And if it changes from negative to positive, then we're talking about a minimum. And that makes sense, right? Because if we draw a quick sketch over here, that's what a maximum looks like. That's what a minimum looks like. The slope is going to change from positive to negative, or from negative to positive, respectively. So let's keep going. Find the intervals where f is increasing and decreasing. Identify all points that are relative maxes and mins, and justify your answers, and then use your results to sketch a graph. Okay. So we need to first of all find the critical numbers. So we find the first derivative. 1/3 times 3 is 1x squared minus 2x minus 3. We set that equal to 0. And that can factor. So we have 0 equals x minus 3 and x plus 1. And we have the critical numbers of 3 and negative 1. So the next step is to figure out if the slope or the derivative changes from positive to negative or from negative to positive at each of these points. So I'm going to set up a almost number line here and only put the negative 1 and the 3 on it, the two critical numbers. And I'm going to label this number line as f prime of x. So what I want to know is, between negative infinity and negative 1, are we increasing, is our first derivative positive or negative? Between negative 1 and 3 is our first derivative positive or negative. And between 3 and positive infinity is our first derivative positive or negative. So let's take a look back at the first derivative. let's plug in 0, something between -1 and 3. So it's 0, minus 3. That's -3. So this is negative. That means any number between -1 and 3 is going to be negative, have a negative result if we plug it into this. Let's try plugging in 4. We'll get 4 squared is 16 minus 8 minus 3. So we'll get 5, so that's positive. And something below -1. So if we plug in -2, we get 4 plus 4, 8 minus 3 is 5, so it's positive again. Okay. So anything between -1, infinity and -1 is going to have a positive first derivative. Anything between -1 and 3 is going to have a negative first derivative. Anything from 3 to infinity is going to have a positive first derivative. And so if we take a look back up at our rules here, that means that this -1 is a maximum because it changes from positive to negative. And the 3 on the original function's graph is going to be a minimum because the slope changes from negative to positive. I'm supposed to sketch this, so we need to actually find the points. So I'm going to plug -1 and 3 into the original equation to see what we get. So if I plug -1 in here, the original f of x, I'm going to get 11/3. And if I plug 3 in, I'm going to get -7. So then if I sketch this, I'm going to count by 2's on the y-axis. And I'll just count by 1's on the x-axis. So we have a point at -1, 11/3, 3, 6, 9, 10, 11. So it's close to 4. And 3, -7. This is a max, so it's going to look like this. This is a min, so it's going to look like this. And then we just have to connect it without making any more maxes or mins. So this is a rough sketch, so it's not going to look exactly like the real graph. But it has the right maximums and minimums, so that is good enough for this question. We're doing a rough sketch. All right, let's keep moving. Next up, we're going to find the intervals where this new function f is increasing and decreasing. Identify all points that are relative maxes and mins, and justify your answers. Use your results to sketch the graph. Okay, so the first thing that I think of when I see a piecewise function like this is I want to know, is this function actually continuous? Do we have a function where between these two sections we connect? So in order to figure that out, if we're continuous, we're going to set 2x plus 1 equal to x squared minus 2 and see if that's true, specifically when x equals 1, because that's where they meet. This is continuous, so we just need to figure out if they're continuous where they meet. So I'm going to plug in 1 for x. And I end up with, what did I do wrong? Oh, we care about -1, not +1. They meet at -1. I misspoke and said it was +1. So we have -2 plus 1, which is -1. And -1 squared is 1, minus 2 is also -1. So that's true. So yes, this is continuous. So that's a good start. So now we need to find the intervals where f is increasing and decreasing. So this really has kind of two pieces here. We're going to talk about f of x equals 2x plus 1 on this side, and f of x equals x squared minus 2 on this side. So over here, if we take the first derivative, we get 2. So that is definitely increasing from negative infinity to infinity because the slope is always 2. Slope's always positive, so the original function's increasing. The first derivative of this guy is 2x, and if we take a look at the number line here, we have a critical point at 0, because 0 will make the first derivative 0. And if I plug in any number that's positive in here, it'll give me a positive answer. Any number that's negative, I plug it in here, I'll get a negative answer. So what that's telling me is that this function is decreasing from negative infinity to 0 and increasing from 0 to infinity. So now we want to combine these again, taking into account this part over here. So the function as a whole is, when x is less than or equal to -1, we have this going on. So we know we're increasing from negative infinity to -1. Then when x is greater than -1, we have this part. So from -1 to 0, we're in this decreasing section. And then we're increasing again from 0 to infinity. That whole region here is included in our interval, right? Because this is for x greater than -1. So here's our combined increasing and decreasing behavior. Now we want to find all of the points that are relative maxes and mins. Okay, so let's figure this out. We already know that we have a critical point at 0. And we also change from increasing to decreasing at -1. I could write this on the number line like in our previous question if we wanted. And we could say that -1 and 0 are where we switch. And so from -1 to 0, we have a negative slope for the first derivative. From 0 to infinity, we are positive again. And from negative infinity to -1, that's this part over here. We're increasing, we have positive slope, positive first derivative. So this and this are going to be our extrema. So in this case, we have positive to negative, so this is a max, and negative to positive, so this is a min. We wanted to identify all points that are relative maxes and mins. So we're going to have to find the y values. So if we plug in -1 up here, it goes in this one. We have 2 times -1 is -2 plus 1 is -1. And if we plug in 0, it goes in this one. 0 minus 2 is -2. So we have a relative max at -1, -1, and a relative min at 0, -2. So now we're going to try to sketch this. And I know I have a relative max at -1, -1. And I know I have a relative min at 0, -2. Based on the original equation, I know that for x is less than or equal to -1, we're just the line 2x plus 1. So we have a slope of +2. So it's going to go down 2, left 1, down 2, left 1, etc. And then for x is greater than -1, so all of this over here, we're at x squared minus 2. So that's parabola. This is the minimum. So we're going to look like this. I could sketch a couple more points if I wanted to. If I plug in 1, I get 1 minus 2 is -1. If I plug in 2, 2 squared is 4, minus 2 is 2. And that's enough. I'm going to now connect the dots. And it looks like this. And that matches up with what we said, right? We're increasing from negative infinity to -1. We're decreasing from -1 to 0. We're increasing from 0 to infinity. We have a relative max at -1, -1. We have a relative min at 0, -2. All right? There we go. Cool. Let's keep going. Use the graph of f prime to A, identify the intervals on which the graph of f is increasing and decreasing, and B, estimate the values of x at which the graph of f has a relative max or min. Okay, so this is a graph of the first derivative, part A. We're going to figure out where are we increasing or decreasing. So it's not where this graph is increasing or decreasing. This is the slope of the original. So whenever this is negative, the original is decreasing. So we're decreasing from negative infinity to negative 3. We're increasing wherever this is positive. So from negative 3 to 1. Then we're decreasing again from 1 to 4. 1 to 4. And then we're increasing again for numbers greater than 4. All right, for letter B, we're estimating the values where we have a relative max or a relative min. So at negative 3, the slope changes from negative to positive. So negative to positive means that we have a minimum. At 1, we're changing from positive to negative, so that's going to be a maximum. And then at 4, we're changing from negative to positive, so that's going to be another minimum. All right, and this is happening because the first derivative is changing from negative to positive, and this is happening because the first derivative is changing from positive to negative. It does say to justify your answers, so you may want to write an explanation for those, but I'm going to leave it like that. Okay, next up is concavity. Let f be a function whose second derivative exists on an open interval I. If the second derivative is greater than 0, then the graph of the original function is concave up. And if the second derivative is less than 0, we're looking at a concave down initial graph. Right, and concave up looks like a smile. Concave down looks like a frown. I usually remember that by thinking of, like, if you're up, you're positive, you're looking good. If you're down on life, you might be frowning because you're looking down. Whatever, however you remember that. It's curving up, it's curving down. That's what that means. Okay. And that brings us to inflection points, which are basically the second derivative version of critical numbers and critical points. An inflection point is if the second derivative of c equals 0, or if the second derivative of c does not exist, and the second derivative changes sign from positive to negative, or negative to positive at x equals c, or if the first derivative changes from increasing to decreasing, or decreasing to increasing. Now, these last two lines really just mean the same thing, right? If the second derivative is changing signs from positive to negative or negative to positive, it means the same thing as the first derivative changing from increasing to decreasing or decreasing to increasing. It's the same thing. The inflection points are more particular than the critical points. Critical points don't care about changing sign. They're all critical points, even if the sign doesn't change. Inflection points have to have changing sign included before they're declared pure inflection points, okay? So let's take a look at a couple examples here where we are going to dig into concavity and inflection points. First up, the graph of f is shown below. State the signs of f prime and f double prime on the interval 0 to 3. So if we're looking at this whole interval, f prime is the slope, right? So the function is decreasing, so the first derivative is negative. The second derivative, however, we have an upward curve here. This is concave up. So the second derivative is positive. In other words, concave up. That's going to bring us to the next example. Given the function f of x equals x to the fourth minus x to the third. Okay, we have quite a few things to find here, so let's try this. We'll start with A. The intervals where f is increasing and decreasing. So that's going to be kind of back from our critical points. So we're going to have our function, which is x to the fourth minus 4x cubed. And we take the first derivative, which will get 4x cubed minus 12x squared, set it equal to 0. And we'll have to find where the x values that work here. So I'm going to factor out 4x squared, and I get x minus 3. So we have x equals 0 and x equals 3. If I make a number line here and only put 0 and 3 on it, we're looking at the first derivative sign chart. If I plug in something like 1, I'm going to get 4 minus 12, it'll be negative. If I plug in 4, it'll be 4 cubed times 4 minus 12 times 4 squared. It's going to be positive. If I plug in a negative number, this is going to be negative minus a negative. So that'll also be negative. So what this means is that we are decreasing from negative infinity. You know, we might pause here for 1 second, but it keeps decreasing. So it goes all the way to 3, decreasing. And it's increasing from 3 to infinity. Technically, I think we might want to include a break there. So I'm going to actually edit this answer. For the decreasing part, I'm going to put negative infinity to 0, u, 0 to 3. Because actually at the 0, we're going to have a horizontal tangent line. So it's technically stable for that exact point and not decreasing. I don't know. We can argue that in class if you want. But let's move on to letter B. The relative extrema. So we're going to use that information that we just found. And the 0, the slope doesn't change from negative to positive or positive to negative. So we're only going to have a relative extrema at 3. So we need to find f of 3. Which is going to be negative 27. And since it changes from negative to positive, it's going to be a relative minimum at 3, negative 27. Letter C, the intervals of concave up and concave down. So now we need the second derivative. I'm going to go back and look at my first derivative, and we're going to take the derivative of this. So it's going to be 12x squared minus 24x. I'm going to set that equal to 0. And I can factor out 12x. And I set those factors equal to 0. I'm going to get x equals 0 and x equals 2. So I make my second derivative sign chart. We have 0 and 2 on this. And let's think about this. So we have to plug these numbers into the second derivative. So if I plug in 1, I'm going to get 12 minus 24. That's negative. If I plug in 3, I'm going to get 12 times 3 squared minus 24 times 3. It's going to be positive. If I plug in a negative number, this will be positive, and this will also change positive. So that's going to be positive. So I'm going to have to write it up here. We're concave up from negative infinity to 0 and from 2 to infinity. And we're concave down from 0 to 2. Okay. Letter D. Inflection points. So inflection happens, remember, whenever the second derivative is 0 or doesn't exist, and the second derivative changes sign. So this happens twice. At 0, the second derivative changes sign, and at 2, the second derivative changes sign. So we're going to use 0 and 2, and we're going to plug those into the original function, and we're going to get 0, 0. And if we plug in 2, we get negative 16 as the y value. Finally, this question tells us to sketch a rough sketch of the graph of f. So here we go. There's 1, 2, and 3. And let's see, we have a point at 0, 0. We have a point at 2, negative 16, and 3, negative 27. So I'm going to have to get a little bit creative here. So 2 is negative 16, 3 is negative 27. All right, so now we have to think about the concavity and the maxes and mins. So 3 is a relative min. There's no other maxes or mins, so it must go up this way and up that way. Our concavity is concave up from negative infinity to 0. So it's going to look something like that. Concave down until we get to 2. And then concave up from 2 to infinity. So it looks something like that. We have concave up, concave down, and then concave up again. And that's the best graph that we can make based off of this information. All right. We made it. Let's keep going. Next up, we're going to look at the second derivative test. The second derivative test says that if f is a function such that the second derivative of f exists on an open interval containing c, if this first derivative is 0 and the second derivative is greater than 0, we're looking at a minimum. And if the first derivative of 0 and the second derivative is less than 0, we're looking at a maximum. All right, so this is just a different way, instead of using the critical numbers and checking the first derivative on either side, if you just check if the second derivative is positive or negative, it works out. Because think about this. If we know our first derivative is 0, we know already that it's a min or a max. And if the second derivative is positive, it's telling you it's concave up, so it would become a minimum value. We know we're concave down, and we know that our first derivative is 0, so we have a horizontal tangent line. That's going to be a maximum because the curve forces it to be a maximum. There's no way you can make a minimum on a curve that is concave down the whole time. It doesn't work. So let's try this. Using this version of the second derivative test, if possible, find the relative extrema. So we're going to use the first derivative and the second derivative of this function. All right, so there's our first derivative and our second derivative. We are going to check where the first derivative equals 0. So let's do that first. I can pull out 15x squared. And we get x equals 0. If I solve this for x, I get x equals plus or minus 1. So now I need to check the second derivative at each one of these x values to see if it's positive or negative. So I'm just going to make a chart with x and the second derivative of x. So let's try this. So the x values I'm interested in are -1, 0, and 1. And I'm looking for the second derivatives. So I'm going to plug each one of these into this. So if I do that, I'm going to end up with 30, 0, and -30. So if the first derivative was 0, which is true for all of these, and the second derivative is positive, then we have a minimum. And if the first derivative is 0 and the second derivative is negative, we have a maximum. If it's 0, we don't have a min or a max. So that's our minimum and that's our maximum. If we wanted the actual ordered pairs, it would be -1, -2 when we plug into the original function, and 1, 2 when we plug into the original function. All right, so we did it. Let's keep going. Suppose that the function f has a continuous second derivative for all x, and all of these things are true. There's a g function as well, and its derivative is given by this function given for all x. Does g have a local max or a local min at x equals 3? So let's think about this second derivative test. We want to know if we have a first derivative equal to 0 and if our second derivative is positive or negative. So let's check all of those things here. This is going to be a little bit tricky, but we got this. So first, we're given the first derivative. So let's just check the first derivative at 3 to make sure it equals 0. So we're going to plug in 3 for all of the x's. And 9 minus 9 is 0, so 0 times whatever is going to be 0. It doesn't even matter what that part is. The first part equals 0. So yeah, it's 0. So we do know the first derivative was 0. So now we have to check the second derivative, which we don't have yet, so we have to find it. So this might be a little tricky. We have a product, so we're going to have to do the product rule. So it's the first times the derivative of the second. Let's see what this becomes. So we're going to have 2f prime of x plus 5f double prime of x. We don't have any chain rule to do here because the inner functions were just x. Okay, and then we're going to add the second times the derivative of the first, which is going to just be 2x plus 0. And so that's what we've got, and now we're going to plug in 3 and see what happens here. So we're going to get 3 squared minus 9, 2f prime of 3 plus 5f double prime of 3 plus 2f of 3 plus 5f prime of 3 times 2 times 3. So this whole thing is multiplied by 0. So that's all just going to be 0. Don't even care about those things. Plus 2 times, what's f of 3? F of 3 is -4. Plus 5 times f prime of 3, which is 1, times 2 times 3. So we have -8 plus 5 times 6, which is what? -3 times 6. We get -18 for the second derivative. So our first derivative is 0, the second derivative is negative. So that means we have a local maximum. Because g prime was 0 and g double prime was less than 0. All right, so that's that question. Let's keep going. All right, this whole page is an extension of one initial question step. We have a graph of f prime. This whole section is just about like comparing graphs of f prime, and f double prime. And this is the last question for the notes. So the graph of f prime is given. The domain is from -3 to 3. For what values of x, -3 less than x less than 3, is the graph of f increasing? So think about that. F is increasing when f prime is positive. So this graph is positive from -3 to -2, from 0 to 2, and from 2 to 3. that means that the first or the initial function is going to have a positive slope, which will make it increasing from here, here, and here, okay? For what values of x does the graph have a relative maximum? Relative maximum occurs when the first derivative changes from positive to negative, right? So positive to negative happens at x equals -2 only. And that's because f prime changes from positive to negative. Letter C, for what values of x is the graph concave down? Okay, so now I have to look at this graph. If we're looking for concave down, it means the second derivative is negative, which means that the slope of the first derivative is what we're looking at, right? So the slope of the first derivative is going to be the second derivative. So we want to have a negative slope on this graph. Or where is it decreasing? And it's decreasing from -3 to -1 and from 1 to 2. If we took the derivative of this graph, that's where we would have negative values because that's where the slope is negative on this graph. So that's where the second derivative is negative. That's where the initial graph is concave down. Letter D, for what values of x does the graph of f have an inflection point? So remember, an inflection point is when the second derivative is 0 and the first derivative, the second derivative is 0 and the second derivative changes sign. So let's check that. So look back up at this graph. Our second derivative equals 0 whenever the first derivative has a horizontal tangent. So that's happening here, here, and here, right? If we take the derivative of this, that's where we're going to have zeros. So it's going to be at x equals -1, x equals 1, and x equals 2. And let's figure this out. What's happening to the second derivative? Is it changing sign? So is the first derivative changing slope? So it's from negative to positive. At 1, we're going positive to negative. And at 2, we're going from negative to positive. Okay, so all three of those change signs on either side of the 0 of the second derivative of the inflection point. So all of those are inflection points. And that is it. We made it to the end. Thank you so much for watching, and let me know if you have any questions. Thank you.